All right, so that's number one. Number two and then number three, it was, I think was okay. Same thing with number three. If you have any questions, you should come talk to me on those. All right. As a reminder that we're going to have another quiz this Thursday about the same time, starting 7:30 and to 8 o'clock. So that will be, for now, the plan is that the quiz will cover, so quiz on Thursday covers 6.2, 6.3, and the 7.1. If we don't cover enough, we will not put 7.1 on it, but keep in mind that it might be on it. We already talked about 6.2, which is the to find the volume of a solid when you rotate an area over a certain axis using the disk method or the shell method or the washer method. So today we're going to finish 6.3, which is called the method of the shell method, which is basically you take any volume, any solid, right, from rotation or from rotating a area, any solid. If you kind of think about the solid as a lot of cylinders with the wall thickness. If you take a lot of them, you put them, put the smaller one inside the big one, and that's what that's what will give you the volume. So as you can see, here's the solid, but if we just treat it as the solid is made of a lot of cylindrical shells, then you kind of get this estimation on the right. So generally speaking, I'm trying to shade this sort of this cross section right in the middle of that solid. Hopefully it's not as confusing. So if you think about, if we take that area and then we rotate around the y-axis, we get the solid on the left. But then each of the cylindrical shell in the picture on the right is sort of coming from you taking a rectangle from that shaded region, and then you rotate that just one rectangle around the y-axis. So if you do that, all of what we get after we rotate that small rectangle. So we get this sort of cylindrical shell. Right? So that's the shape we got if we just rotate one rectangle around y-axis. That shape I draw in black, that's sort of equivalent to just one of the cylindrical shells in the solid on the right. So imagine there's a lot of them. You put the smaller one in the big one, and then put the one in the next size big one, so you end up with a solid. So that's how we use shells to estimate the volume. So if we add up all those volumes of each shell, then we get the total volume. Basically, that's the idea. Now, how do we find the volume of each one shell? So to find volume of just one of them, not all of them, one shell. Well, to find the volume of one shell, we can imagine that we taking the shell. So let me redraw that shell in the middle there. So if we take this shell in the middle, and if we cut it open along one side, so we cut it open there, and then we open it, we should end up with this rectangular shape with the thickness . So that's the shape we get when we cut the one shell, the cylindrical shell open, and then just open it up. That's what we get. That will help us find the volume for one shell. And let's just consider this shell here. This shell is a cylinder, so it has a radius, let's call it R, and it has a height, let's call it H. Now, when we cut it open, the height will become the height of this rectangular prism. And then the length of that rectangular prism, that will be just a circumference. If you're familiar with this, if you take a piece of paper, right? We'll roll it into a cylinder. If you roll it into a cylinder, that's what and imagine that's a thickness to that cylinder. So that will be the shell. But if you cut it open in the middle and then you open it up, you get a rectangular prism. And that rectangular prism has a thickness. And this is the height of the cylinder. This is just a circumference. If you kind of roll it, that's just the circumference of the cylinder. If you cut it open, that becomes the length of the rectangular prism. If you're not familiar with that, just take a piece of paper and roll it into a cylinder to take a look at that. So the base here is just the circumference of the cylinder, which is 2 pi times the radius. And then you still have the thickness to this. Right? And then the volume, so that will give the volume. So the volume for one shell, that's just length 2 pi r times the height, h, times the thickness. That will be the volume of one shell. And if you add up all the shells, so basically you integrate that, you get the volume. So the integral basically means you add up all the shells you get, and then you get the total volume. I hope that kind of make a little bit of sense. In a more correct notation, so if we see the thickness, going back to the first diagram here, so if we call the thickness of the shell, of one shell, let's call it dx, because it's in the direction of x. So if we call that dx, this is the thickness, and then we can write the volume using the shell method. We'll be integrating. Let's call this as A, this is a B. So from A to B of 2 pi r, that will give you the length, the circumference of one cylinder. So that's the length of the rectangular prism when you open it up, times the height, which is the same thing, the same height as the height of the cylinder, also the height of the rectangular prism. So times the height, and then times the thickness. The thickness here is just dx. R is the radius. So that's the formula to get the volume. Does that sort of make sense? So in problem like this, you always want to take the shaded region. You figure out a rectangle that you're going to rotate. Just pick any rectangle in that shaded region. You're going to rotate around the axis. And then that will give you a sort of a cylindrical shell, just one of them. And then you can find the volume for that by imagining you cut it open, make it into a rectangular prism. So that's what this part is. This gives me the volume of just one of them, one shell. And then if you integrate, that will give you the total volume. Is the thickness equals radius? No, the thickness is just the thickness of the shell. In this case, it's this bottom part of that small rectangle. So that's just kind of either going to be dx or dy. So that's what thickness is. It's always going to be one of those two. Depends on the direction that you pick the rectangle to be. So that's a thickness. All right, I'm going to use one example, hopefully to make a little bit more sense. So here's this example. So it's this shaded region bounded by y equals square root of x. And then y equals 0, which is the x-axis, and also x equals 2, which is this green line on the right. And then we're going to take this region and we're going to rotate it around the axis, x equals 0, which basically means it's y-axis. That's what we call x equals 0. So we're going to rotate that solid about this axis. So if we rotate it correctly, we have done this before, we end up with this let me use a gray color there. So at the bottom, it's a circular base. The top is also a circular base. But then in the middle of the top, you get like this shape that's missing. If you try to picture the shape, you only get the sort of the wall, but then the middle is like hollow there because of the cone shape we got by rotating y equals square root of x. Right? So we want to find the volume of this shape. Well, to do that, we're just going to imagine we rotate it instead of the entire area. We imagine we're rotating a rectangle. So imagine there's a lot of, so imagine we're rotating a small rectangle from this shaded region. And when we rotate that rectangle about the same axis, the y-axis, we end up with this sort of shell-like, I mean, it's still a cylinder, small cylinder in the middle. But we get this like a cylindrical shell shape in the middle there. So if we get a lot of this, so if we take this rectangle, we rotate it, we get, again, a shell. And if we take this rectangle, we rotate it, we get a shell. Doesn't matter, right? We got a lot of shells. If we stack them together, we get the solid. Let me erase this. So that's the idea. So let's just focus on this one cylindrical shell that I have in the middle. I'm going to copy it down below here. So this cylindrical shell, it has a thickness, just the thickness of the wall. And the thickness from the diagram is just dx because it's basically the base of the rectangle. That's what the thickness is. And how do we find the volume of one of the shell? If we cut this open, we basically end up with a rectangular prism. This part is just the circumference of the cylinder. So this is 2 pi r. This part is the height, same height as the cylinder. And then obviously that's a thickness that I'm not drawing to the rectangular prism. Well, let's find out the radius and also the height because, well, we have the thickness because we need that for the volume. So the volume from here says that it's integrating from A to B, 2 pi times radius times height. of that cylindrical shell times the thickness dx. So let's find those out. So the radius of the cylindrical shell, so that's the radius. On the diagram is the distance from this y-axis go all the way to this point. Let's call that x. We don't know what it is. It could be any x value from 0 to 2. So that's the radius. Let's just call that x for now. So now we have volume is equal to integrating from a to b. We're going to figure out a and b later. So 2 pi times the radius. The radius in this case is just x times the height of that cylinder. The height, that's the height. In the solid, the height is given by the distance from this red curve go all the way to the x-axis. So that's the height. Well, we know here it's given by y equals square root of x. That's what that red curve is. So the height is just a y value, or we can write square root of x. So that's the height. Let me finish this, then I'll explain why. And then the thickness we already talked about, that's just dx. So why is the radius x? Because the radius is the distance from, we pick the rectangle to be here. Let's call this part, let's call it x. I'm getting too much lines here. So if we call this point has an x value x, then from the y-axis to that point, that distance is just x, right? It's x minus 0, so that distance is x. So that's what the radius is. So the radius is x. It's not a fixed value because the rectangle we can pick anywhere. In this case, we just pick in this location, but we don't know exactly what the x value is. So we use x instead. So the radius is given by the distance from x equals 0 to that point. So it's just x. Any other questions before I move on?
Could you explain one more time why radius is r?
Well, radius I just represent radius, right? So I is just arbitrary variable I'm using to represent the radius. In this example, the radius for this specific cylindrical shell that I'm picking, the radius is the distance from the y-axis goes all the way to where I draw the rectangle in the beginning. So that distance, that's the radius, right? If you imagine we're rotating that small rectangle I had, if I rotate it around this y-axis, right? So that's what the radius of rotation is. It's also the radius of the cylindrical shell in this example. But how long is that? I don't know exactly because I don't know the x value of the rectangle, the base of the rectangle. I don't know where the base of the rectangle is located, but I know it's somewhere on the x-axis, right? So I'm just going to say, okay, that rectangle's base is located at the point just x on the x-axis. That's exactly how we define the x-axis, right? So if you have 0, 1, 2, 3, what do we call this point? We call it x. We don't know exactly what it is, but we can use x to represent that value on the x-axis. So that's the radius. And then the height is just given by the distance from the red function y equals square root of x to the x-axis. to the x-axis, so that distance is just square root of x. Now, what's the boundary, what's the upper bound and lower bound that I'm integrating from? What's the a and the b? Well, since we're integrating with respect to x, so we just look at the x intervals of the shaded region. That shaded region we begin with goes from x equals 0, go all the way to x equals 2. So the upper bound and the lower bound will be just 0 to 2. That's the a and the b value. And the rest is about finding the antiderivative and then evaluating the integral to figure out the volume. I'm going to write one more step. So 0 to 2, 2 pi x times square root of that x, that's x to the 3/2 dx. Then you have to find the antiderivative. You can always bring out the 2 pi, so 2 pi from 0 to 2, x to the 3/2 dx. I'm going to let you finish that because you have to know how to find the antiderivative from that. Any questions on this example? So try to picture that the cylindrical shell, you got it by rotating a small skinny rectangle in that shaded region to get this cylindrical shell. It's a cylinder with a thickness. All right, here's the next example. In this example, so we're going to take this shaded region and then we're going to rotate it about the x-axis. So we're going to rotate around this axis. When we rotate that, we end up with this solid. So it's similar to what we had before, but now this solid has a circular base in the vertical direction. But then in the middle, it's hollow. So that's the shape. Well, how do we get a cylindrical shell from here? Because we're rotating around the x-axis, so when you pick a rectangle, you have to pick it so that the rectangle is parallel to the x-axis. So I'm going to pick the rectangle in this direction, so that when I rotate this rectangle about the x-axis, I end up with this cylindrical shell in the middle. Oops, I didn't draw it correctly. So that should be the cylindrical shell I have in the middle in this diagram. So imagine you get a lot of this sort of horizontal cylinders, and then you kind of piece them together, you get this solid from rotating the shaded region. And I'm going to redraw the cylindrical shell on the side. And in this example, the thickness of the cylinder is not in the x direction, right? So the thickness is given by, this is what the thickness is. So that's the thickness of the shell, which is in the y direction. So that's dy, not in the x direction here. And then this part is the radius. We have to figure out what the radius is for this cylindrical shell. And then this, you can think about it's a height. So this is the height, but I'm going to label it at top here. So I'm going to call this is the height of that cylindrical shell, of the cylinder. It's just sideways cylinder. If you kind of rotate it 90 degrees, you get the same shape as before. So how do we find how do we use this to find the volume? Well, if we imagine we're cutting this cylinder open, if we cut it open here, then we end up with this, again, a rectangular prism with the thickness, it's the same thickness there. That doesn't change, which is dy. And then this measurement on the side, the height of this rectangular prism, in this case, you can think about the vertical distance. This is 2 pi r, because if we cut it open, we roll it, you know, you kind of get this like a rectangular prism. So that this measurement is 2 pi r, and then this part is the height. It doesn't really change anything, just a different orientation. So the volume here is given by integrating again from A to B. We're going to find out A and B later. But the volume for one cylindrical shell, again, that's the same setup. So that's the 2 pi times the radius. And I'm going to figure out what the radius is times the height times the thickness. That doesn't change from A to B. And then let's find those values. Well, 2 pi doesn't change. What about the radius here? In the solid I draw here, I labeled this is the radius. Exactly. So the radius is just the vertical distance, right? If you want to know what this value is, that value we don't know, but we can call it y, because this is what the radius is. We don't know what that is, but we can just call it y. It's on the it's a value in the y direction, so we can call it the y. So we can just call this y. We don't know what it is, but we can just call it y. So that will give us a radius. It's from y value to y equals 0, right, to the x-axis. So this distance, that's a radius, we can call it y. What about the height? The height is given by this horizontal distance that I'm marking in red. Right? That distance, I can imagine it's just the distance from this curve, y equals square root of x, to the y-axis. But how do we describe that height, that distance? So we know the height is given by the distance from y equals square root of x to y-axis. So that's the distance, will give me the height of the cylinder. I can't just use y directly, because y is a vertical value. So here I have to use a horizontal value, x, instead of the vertical value, y. So I have to rewrite the first function as x equals y squared. The second axis, y-axis, right, as x equals 0. So the distance between them will be just y squared minus 0. That's what the distance is. It's sort of the distance between the two x values, right? The x value on the left is x equals 0. The x value on the right is x equals y squared. So that's the distance. The distance between the two x values give me the height of the cylinder. So y squared minus 1 minus 0. That's the height. And then the thickness is dy, which we talked about at the very beginning. And what about the upper bound and the lower bound? That just going to be the two y values, because we're integrating in y direction. So the upper bound and lower bound will be the y interval for the shaded region, which goes from y equals 0, go all the way to this green line. And if you recall, we've done this before. Since the curve is y equals square root of x, stops at 2. So this y value at the top, this green line has a y value, y equals square root of 2. So that will be just from 0 to square root of 2. That's a lower and upper bound of interval. You can drop the -0 there. Just rewrite it one more step. Integrating from 0 to square root of 2, bring out 2 pi if you like, or just leave it in there, doesn't matter, y times y squared dy. Can you explain how did I get the height again? So in this case, the height, it's because the cylinder is laying horizontally, right? So the height is just going to be the length, the measurement that I'm marking in the red segment here. So that will be the height. And that height is given by the distance between the red function, y equals square root of x, because the right side of the segment length on y equals square root of x, and the left side of the segment length on y-axis. So it's just going to be whatever the distance between those two functions. Well, because the segment is horizontal, so we're comparing horizontal distance. So we can imagine that we basically need to know this x value and then this x value. So if we know the difference between them. So basically, whenever you want to know how long this segment is, right? This is x-axis. If you want to know what this distance is, you go to the x values and find the difference among the x values. Right? For example, if this is x equals a, this is x equals b, so the length of that segment is just b minus a. That will give you the length of the segment. In this case, we don't know b, we don't know a. I'm using a different a and a b here. Probably not a good. Let's call this capital A. That's capital B. So capital B minus capital A, that will give me the length of that horizontal segment. But I don't have exact values. In this setting I have here, I have this x value is given by the function y equals square root of x, but I need the x value. So I have to write as x equals y squared, and I use y squared there. On the left, I get y-axis, which is equivalent to x equals 0. So I have to use x equals 0 for the value on the left, and the y squared for the value on the right, and to find the difference between them. In this case, will be y squared minus 0. So that will give me the horizontal length of that segment, which is the height of the cylinder. I hope it's difficult to explain this. I'm probably not doing a good job, but I hope it sort of make a little bit more sense. So that's the height of the cylinder, and after you found it, you just use it in the formula directly. Sorry, radius. Any other questions? Okay, so one more example. So in this case, we're going to find the volume of the solid obtained by rotating the region. Again, this region, just like the region above. And in this time, we're going to rotate it about the y-axis. if we do that, we end up with this. So we still have a solid, so the top will give us a circular base. And at the bottom, it's a cone shape. So the overall shape is basically, it's a cone, it's sort of like a cone pointing downwards. The top is a circular base, right? The bottom is a pointed tip. And if we want to get a cylindrical shell out of this, you cannot, so I'm going to erase this. So if you draw a shape, draw a rectangle this way, don't copy this down, I'm going to erase this. So if you draw a rectangle horizontally, when you rotate it, you're not going to get a cylindrical shell, right? You just get a disc. But we don't want a disc. We want to practice using the shell method. So if you draw it like this, you're going to end up with a cylindric, you're going to get a circular disc, but that's not what we wanted. So what we need is that we need to draw the rectangle in the opposite way. So we're going to draw the rectangle this direction. And if we rotate this rectangle around y-axis, we will get a cylindrical shell. I hope that kind of makes sense. So that will be a cylindrical shell in the middle. And if you cut this open, you get a rectangular prism. With the thickness. Now, what is the thickness? Because of the rectangle I draw in the beginning has a base in the x direction, so that's the thickness. That's how thick the wall is. That is just changing x, so I'm going to call this dx. That's the thickness. Now let's figure out the radius and also the height of the cylindrical shell. So that's a radius. And in the drawing I have, so this is the radius, right? So just like before, the radius here is given by, so radius is equal to the distance between the red curve and the y-axis, between y equals square root of x and the y-axis. So that will be the radius that I'm rotating the small rectangle. You always, so that's, you kind of have to decide, right? You figure out what the solid looks like, and then you always want the cylindrical shells, right? So you have to figure out, how do I draw the rectangle to get a cylinder, right? So basically the idea is that if you rotate around, if you take a region, rotate it around x-axis, so you have to draw the rectangle horizontally, so that when you rotate around x-axis, you get a cylindrical shell. If you rotate it around y-axis, like we did in the first example and also the one I'm working on now, if you rotate around y-axis, you have to draw the rectangle vertically, so that when you rotate around y-axis, you get a cylindrical shell. Here it's the same. So I'm rotating the shape around y-axis. I'm going to draw the rectangle vertically, so that when I take a vertical rectangle, right, you rotate around y-axis, you get a cylindrical shell. Mhm. Any other questions? So here, let's continue to find the radius. So the radius is distance between y equals square root of x and the y-axis. Well, that distance, if you recall, we can just treat it as the x value, right? We don't know how long this is, but if we call this x, if we call this point, this value x, so the segment is just given by the x value. So that's the radius. We can just call it x. It's a horizontal distance from 0 to this x value. I don't know what that is. I'm just going to call it x. So that's a radius. Now, what about height? This is the height. In this case, height is a vertical measurement. So in the drawing, this is my height, the one in purple. So that's a height. How do I find the height? The height is equal to distance between the segment, the green segment at the top. That one, you should know by now, that one is just y equals square root of 2. That's what this green line is based on what we've done in previous problems. So this is y equals square root of 2. So the distance between that line, y equals square root of 2, and also the red curve, y equals square root of x. So that distance will give me the height of the cylinder. So this is a y equals square root of x. This one is y equals square root of 2. So whatever the difference between those two, the vertical distance between those two curves will give me the height. And that's just, since we're looking for vertical difference, we just subtract the two y values. So that's a square root of 2 minus square root of x. How do we know whether to use a cylindrical shell method? Normally, you can decide whichever you prefer. Like, you know, if I don't see you have to use a certain method, you can use any method. You can use a disk method, or you can use the shell method. But for now, I'm just using this example to practice the shell method. You can obviously find the volume using the disk method. If it's not specified, if I didn't specifically say, you know, use the shell method, you can use the disk method or any method that you find it easy. So now we have the radius, we have the height, we can try to find the volume, right? That's all we need. And the thickness we had it to in the very beginning. So the volume is equal to integrating from a to b 2 pi times radius times the height times the thickness, which is just equal to 2 pi. The radius we said is just going to be x. It's just some horizontal distance away from the y-axis. We can call that x. And the height, it's going to be the difference between the two y values, square root of 2 and also square root of x. So that's just square root of 2 minus square root of x. And the thickness is dx. And because the thickness is dx, so the lower and the upper bound for the integral, which is looking for the x interval of the shaded region. The shaded region we begin with, starting with on the left side is the y-axis, so that's x equals 0. On the right side stops at x equals 2. So the lower bound is 0, the upper bound is 2. This will give me the volume when I evaluate. solve this?
We know the.
Go ahead, Aiden. What's your question?
So we know the bounds from the x-axis is from 0 to 2. That's how we know.
Yeah, for the bounds, it's always easy to. I always find it easy to find the lower and the upper bound, because I'm just looking. I find the thickness is dx, right? So I know that at the end my integral will have a dx there. So how do we find the lower and the upper bound? I just go to the shaded region that I was given in the beginning. So the shaded region given in the beginning goes like this, right? So I'm just looking at this shaded region, looking for the lowest x value, which is this x value, x equals 0. And at the largest x value on the right is x equals 2. So that will be the lower and the upper bound. Well, R always, exactly. So Sam, R just, I use R just means it's the radius, right? But you have to figure out what the radius function is. Is it, is it going to be the horizontal distance between two x values, or is it going to be the vertical difference between two y values? That will depend on the orientation of the cylinder. But yes, so at the end, R always going to be some function with x, or sometimes some function of y, depends. You wouldn't have R there, correct? You'll always turn it into a variable that you're going to integrate with respect to. All right, let me finish solving this. So to solve this, the next step, I'm going to pull out 2 pi, and I'm going to distribute the x into the parentheses. That will give me 2 pi integral from 0 to 2 square root of x, square root of 2 times x, minus x times square root of x dx, and that's equal to 2 pi integral 0 to 2 square root of 2x minus x to the 3/2 dx. And if I continue, so 2 pi, just leave it, and then we're going to find the antiderivative of the two terms inside the integral. So that's the square root of 2x become x squared, but you have to divide by the new exponent 2, minus x to the 3/2 plus 1 x to the 5/2, but you have to divide by that, so 1 over 5/2. And then evaluate that from 0 to 2. Obviously, if you put 0 there, everything becomes 0. So just really plug in 2. 2 pi square root of 2 over 2 times 2 squared, minus 1 over 5/2 is 2 over 5, 2 to the 5/2. And then plug in 0, you get 0. So you don't need to subtract anything. And then that will be that will give you an answer. That's the volume. Those kind of problems, if I'm working on this problem, I think the very beginning, try to get the solid in the head, try to figure out what the cylindrical shell, like which rectangle you're going to rotate to get a cylindrical shell, and also figure out the radius, figure out the height, and the thickness. If you have all of those parts, then you can come up with the volume as an integral fairly easily. And then the rest is just using what we know before to evaluate it. All right, any other questions before we move on to the next example? All right, I believe this is the last example on this topic. This example, we're going to find the volume of the solid, so this shaded region, and I'm going to rotate it around x equals 2. So that's a line I'm going to rotate. The shape of that. So I'm going to rotate around this axis. So if I do that, I'm going to draw the shape. not sure how accurate that is, but you kind of get this shape. But at the bottom, the base is a circular base. So it's kind of like a cone shape because the top is a pointed tip. But the base is circular. Right? So how do we draw the rectangle in the shaded region so that we can get a circular, like a cylindrical shell? Well, you want it to be a cylinder when you rotate around this axis, right? So the rectangle probably should be a vertical rectangle, not a horizontal. If you have a horizontal rectangle, I'm going to erase this. If you rotate this rectangle, you basically end up with a circular base. Just it's a circular, it's a disc, right? But we're not looking for that here. We're using shell method, so we need a cylindrical shell. So I'm going to draw a rectangle this way. So if I rotate this rectangle about this axis, x equals 2, that's how I get a cylindrical shell. That's a cylinder, right? So let me draw that cylinder on the side again. So this cylinder, when I cut it open, somewhere in the vertically, if I cut it open there, I get this rectangular prism. And then this is the thickness. We're going to find out how thick that is. So that's the thickness. Can anyone tell me what is the thickness in this case? Is it dy or dx? Go back to the drawing. So this is the thickness. So what is this? What is the thickness in this case? Is it going to be dy or is it going to be dx? Is it going to be, it's not dy, right? Because the thickness of the, so if you imagine you get a cylinder going on here, so the thickness, the wall of that cylinder, that's in the x direction. So let me do this. So if we call this x1, call this x2, the thickness is the distance between the two x values, right? So that's how thick the wall is. It's right, it's just dx. Right, it's the width, that's the difference between the two x value that will give you the thickness. That's dx in this case. So you can also think about, like, you know, whenever you draw a vertical rectangle, the width of the rectangle, that's always going to be the thickness because you rotate that rectangle around. So that's the base or the width of the rectangle you rotate. So that's dx, that's a thickness. Now the radius, so this is the radius. In my drawing, I can use this part as the radius, but I don't like that. I'm going to use the one on the left. So I'm going to use this part to be the radius. Right? How do we find out this radius? Well, that radius is given, so we know that from 0 to this point, this part right, exactly. So this part right here, the one I'm going to use a dotted line. So this dotted part, that's going to be x because I'm going to call this x. So from 0 to x, that distance will be x. But the radius is the extra part. It's a part from x to 2, right? So if we call this x, oops. If I'm called this x value, then the radius is just going to be the distance from the line x equals 2 to the value x. That's equal to distance between x equals 2 and x equals x. You can think in that way. And it's horizontal, so we just subtract the value on the right, the x value on the right, which is 2, minus the value on the left, which is x equals x. So just 2 minus x. That's the radius. It's a horizontal value. It's a horizontal segment. You take the value, the x value on the right minus the x value on the left. Now the next step is to find the height. The height, you can think about it, this is what the height is of that cylindrical shell. And that height is a vertical distance between the red curve and the x-axis. So that's what the height is. Height equals the red curve, which is y equals square root of x, distance between y equals square root of x and the x-axis. So that will be the height. Oops. And the x-axis has the equation y equals 0 because it's a vertical distance. So we'll just subtract the two y values. So that will be the one on the top, which is square root of x, the one at the bottom, which is 0, so square root of x minus 0. That's the height. So now we have the radius, we have the height, we can find out we also have the thickness, dx. We can find out the volume, which is equal to integrating from a to b of 2 pi times the radius, r times height, times thickness, which is, I'm going to find out a and b later, so that will be 2 pi times the radius. The radius is 2 minus x. That's a horizontal distance. Times the height, which is just square root of x. The thickness is px. And because it's px, so now let's find out the lower and the upper bound of x values of the shaded region. That shaded region we begin with goes from, so the shaded region goes from the origin to x equals 2. That's what we begin with, so that the two x values will be just from 0 to 2.
How do we find the height?
Again?
How do we find the radius? My bad.
Oh, the radius, you know, so let's just go back to the drawing, the solid I draw here, right? So the radius of that cylinder, because the center of the cylinder is at x equals 2. So the black segment I draw here at the bottom of that cylinder, that will be the radius, right? So if you think about this, so this is the x-axis. This is the x equals 2. This is the x equals 1. This is a 0. And this part is what I'm looking for. That's the radius. Right? That's 2. I don't know what this first number is, the left end of the segment. I don't know what that is. But because because this part, I can always call it x if we call this x. So that x value represents this measurement. So that's x. While this part is just a remaining part of that 0 to 2 segment. So I want to know what that is. That's a radius. I know the total is going to be 2 units. The first part, before the radius begin, that's x units. So what about the radius, the part corresponding to the radius? Well, this is 2 units, this is x units, and then this part that I'm looking for, that part will be just 2 minus x. That's equivalent to the radius. I hope my drawing didn't confuse you more. So that's what this part is, 2 minus x. It's a horizontal segment that I'm looking for. Any other questions? I gave you a few homework problems. I think there's like 5 of them, or 4 or 5 problems that practice shell method. Some of them has really nice diagrams, so that will help you with those questions. As you work on them, just take a look at the diagram, the 2D diagram, and then try to picture the rotation, and then compare that with the 3D drawing that was given in the problem, and see if you get it right. It's very important that it's difficult to, I guess, to explain that, but it's the being able to imagine that solid in your head, and then the cylindrical shell in your head is very important to complete this problem correctly. Any other questions? For this shell method, the formula is just one formula. This is the only formula that you need for the shell method. All right, I'm not hearing any questions. So definitely work on the homework problems, and I think that will help you a lot in terms of practicing this concept. And I can tell you that this method, so on the quiz on Thursday, there will be problem that you can use the disk method. There'll be problem that you can use the washer method, and there'll be problem that you have to use the shell method to find the volume. So make sure you are comfortable with all 3 different methods. The washer method is basically the same as the disk method. It just in the middle you have a hollow, right? You get a circle that's being removed from the middle. Any questions before we move on? How many questions will be on the quiz? That'll be like 3 or 4, or maybe 5, depends. But again, we're going to try to give you enough time. So I don't think you need to worry too much about not being able to finish it. But definitely make sure that you're familiar with this concept of using either a disk method to find the volume, or shell method to find the volume. I think if you're comfortable with it, the problems actually wouldn't take that long. All right, so the next part is from section 7.1. It's called integration by parts. It's kind of like the substitution method we learned. This is just another technique. But before I talk about integrate, will this be on the quiz? This might be on the quiz, depends on how much we get through. So before I talk about it, before I give you the formula or the procedures to use integration by parts, let me kind of take a step back. Let's just do a little bit of review. If you remember the product rule in differentiation, so if we have f of x times g of x, and then we find the derivative of that, the product rule. If you recall, that just coming from the derivative of the f function times g plus f times the derivative of g function. That's a product rule. I hope we're all familiar with that. Now, with this product rule, what I'm going to do is I'm going to put the part on the right and move it to the left. Just rewrite it. So f prime times g plus f times g prime equals derivative of f times g. Nothing changed there. And then the next step is that I'm going to integrate both sides with respect to x. When I do that, the left side, so remember that two terms, that means I can integrate each part separately. So the left side, I have integral f prime times g dx plus integral f times g prime dx. The right side, when I integrate the derivative of f times g, so you can think about the d dx and the dx and the integral cancels out. It just gives me f times g on the right side. And you probably wonder what's the whole point of doing this, right? Well, the next step is I'm going to move the first term to the other side. So I get integral f times g prime dx. That's equal to f times g minus integral f prime g dx. Now what this is that, so if we let f equals u g prime dx equals v equals dv, so g will equal to, so if we do that, and this g term, so if we integrate both sides, so integral g prime dx, that will be just integral dv equals v. That's what integral g prime dx is going to be g, and also integrating dv, that will give me v. So g and the v are the same because those two are the same. Hopefully that didn't confuse you more. So when I do the substitution, so what this becomes is that if we integrate u dv, just using a new notation dv for g prime dx, that will become u times v minus integral u prime, not u prime, v du. All right, so let me explain it, try to be less confusing. So here we have, I hope you all agree with me, this part just coming from integrating the product rule from both sides and then move the term to the other side. That's just nothing I did there. So the next part is that we're going to use substitution, different from the substitution method we did, but this is just like simple substitution. We're going to call f u, and we're going to call g prime dx, we're going to call it dv. So if I integrate both sides, so if I integrate here, if I integrate both sides for g prime dx equals dv, so I get derivative, hold on, let me move this. So if I integrate both sides, I get integral g prime dx equals integral dv. Right? Now, what is the left side? The left side, g prime dx, when I integrate, I just get g. And on the right side, when I integrate dv, I just get v. Because I had g prime dx equals dv, and then I have integral g prime dx equals integral dv. So that means g and v I got by integrating them, integrate the left side separately from the right side. So I get g and v. So those two has to be the same because the left side are the same. So g equals v. Then now the next step is I just substitute back into the highlighted equation. So the f, so this f function, it just becomes u, and the g prime dv, g prime dx, it just use dv instead, and the f again is u, g is v, that's what we found out. And then the next step, f prime dx, that is just du. So we had, maybe I should write that down too. So we had f equals u, so f prime dx, that's just equal to du. And then again, that's just a substitute, so it's just the derivative on both sides. And the g become v. This is what we call the formula for integration by parts. And then the next step is I'm going to use a couple examples to show you how to actually use this formula. Now, this formula is useful because sometimes when you integrate to a product, you cannot really integrate because you cannot use u-substitution, you cannot integrate directly. What you can do is that you can try to use this approach. Maybe that will help. For example, if I want to integrate x cosine x, x times cosine x dx, if that's what I want to integrate, I cannot use u-substitution. That doesn't work. I cannot integrate directly because it's a product. So u-substitution wouldn't work easily here. So what do? We can try to use this integration by parts method because it is a product, right? So what we can do is that we can say, okay, I'm going to call this u, I'm going to call this dv. Maybe that's going to help. So I'm going to write it. So I'm going to let u equals x. I'm going to let dv equals cosine x dx. This is kind of like the g prime dx equivalent, but I'm just going to call it dv. Now, what I do next is I'm going to find the du from u. So u equals x, so du equals dx. And the dv is equal to cosine dx, so that means I can integrate. So v equals integral of cosine x dx. That's equal to sine x. So v is the integral of dv. Right, so maybe I should write down v equals integral dv, which is integral of cosine x dx, which is sine x. And now I'm going to use the formula. So this integral u dv, remember x is a u, dv is a cosine x dx. So integral x cosine x dx. So this is a dv, this is a u. Using the formula will become u times v. U is x. And the v I found out by integrating dv, so that's a sine x, minus integral of v, v is sine x, and the du is dx, right? Du is dx. So this integral that we're looking for, the one on the left, we found out one part. which doesn't have an integral, so that's a good part. Well, this part still has an integral, so it's not quite done yet, but at least we can integrate sine x directly in the next step. So this can find without too much trouble. So that will be x sine x minus, so what is the integral? What's the integral of sine x? If you recall, that's a negative cosine x. And don't forget to add a constant c at the very end. It's an indefinite integral. So that's the x sine x plus cosine x plus c. So that's how useful this integration by parts is. It allows you to integrate a product or sometimes some expression that the methods we learned before doesn't work. And also to note that we begin with x times cosine x in the integral, that's a product. But after we use the integration by parts formula once, we end up with an expression that's really easy. That's like already, being integrated. So we get one expression that's really nice. The other one, even though it's still in the integral, but it's actually simpler than what we begin with. So let me note. So sine x is simpler than, it's more simple than x cosine x. At least we don't have the product anymore. So that's sort of the benefit of this integration by parts. You take something complicated, you apply the formula, you get one term perfect, the other term, it's simpler. And then you might have to repeat that process a couple of times.
So I'm still a little bit confused on how you got that, the x sine x.
So x sine x, so the middle term that I put a star underneath, that term is just coming from using the formula directly. So the formula says, if we want to integrate the product u times dv, right? And then that is just equal to u times v minus integral of v du. That's what the formula says from integrating the product rule. You don't have to do that. So from now on, you just have to, just remember the formula and use it correctly, right? So in the formula, the first term is u times v. When I say, okay, I'm going to let u equals x, so I know that u will be equivalent to x, and the du is equal to dx by differentiating both sides, and the dv, I'm just going to call it cosine x dx because I want the given problem x cosine x dx to be u times dv. If u is x, so dv has to be whatever the remaining is, cosine x dx, right? And then to find v, I integrate dv. If I integrate cosine x dx, I get sine x, so that's what v is. Right, so the next part is I take those pieces, I'm going to put into the formula, which says the integral of u dv is equal to u times v. So this part is u, and then this part is v. So sine x is like the v part from integrating dv, and then minus v. So this is a v, and then du, this is a du. That's how I get x times sine x, is because the formula says we're going to have a u times v term.
And so when we have dv, we're taking the integral to get rid of the d just to get v?
Exactly, right. So if you recall that the setup I did, at first I wrote u equals x, then I wrote dv equals cosine dx. I put them like not in the same line. I sort of put them in the diagonal direction. So after you write them down, you always want to find du from there because in the formula you need du. You always want to find v by integrating. So here you differentiate, but from here to there you integrate. So you integrate dv to find v, you differentiate u to get du.
So when you find, so you assign u and you assign dv, right?
Exactly.
And then you take the derivative of u to find du, and you take the integral of dv to find v.
Exactly.
All right, thank you.
Yes, and then you, because in the formula, on the right side, on the left side, you get u dv, right? That's what you begin with. But the right side, you need to know the u, you need to know the v, and then you need to know the du. So you have to find the v from dv. You have to find the u, or you have to find du from u, right? So you the left side, you differentiate the right one. When I say left side, I mean this part. You differentiate. Let me just write down, you differentiate. And this part, you integrate. Let me find another example after you write this down, just to practice. Let's see, x. We'll do x squared e to the x. So for you, I would really recommend that you memorize integration by parts formula, the one I shaded in green, because it's one of the major formulas that you will need.
You need to memorize how to get to that formula?
No, you don't have to memorize that. That I just show you. It's also in the book. If you can just look, if you want, you can always look it up everywhere. They explain it. So this formula is just coming from, you take the product rule, then you integrate both sides, then you just move a few terms around until you get to this point. And then now you're just using substitution, just a regular substitution to rewrite it, make it looks like a u dv on the left side, and a uv and a v du on the other side. It's really the same. Those two are the same same equation, same formula. Just one is written in a more common way using u v. The other one is not, is less common. All right, let me use another example. Hopefully that will help a bit. So the second example, I'm going to integrate x squared e to the x dx. So if we use u substitution, it's not going to help us. If you don't believe me, you can try it. Right? And I'm going to put it in box here. So this is what I'm looking for. This one, I'm just going to put in the formula. So if we integrate u dv, that's equal to u times v minus integral v du. That's just a formula. So here, again, I'm just going to pick a u. So I'm going to let u equals, I'm going to call it x squared. So I'm sort of splitting the given expression in the middle. I'm going to call u x squared. And then dv, I'm going to call the rest. So the rest is e to the x dx. So I'm going to call that dv. So the left side, I'm going to differentiate to get du, which is if you differentiate both sides, you get 2x dx. And the dv, we're going to use it to find v. So v equals integral dv, which is integrating e to the x dx. If you're familiar with that, that just give you e to the x. So now I have u, I have du, I have v, I have dv, right? I have all four terms. So I can apply the formula. So the given integral is in the form of u dv. So that's integral x squared e to the x dx. This is in the form of u dv. So applying the formula, the first term is u times v. U is x squared, v is e to the x, and the du is 2x dx, dv is this part. I'm just going to use that directly. So u times v is x squared e to the x. This is good because this doesn't have integral. So we get rid of the integral part for this first term. Minus integrating v. V is e to the x. And the du is 2x dx. So I'm going to put 2x in front and the dx here. Oh, you know what? Let me just rewrite it as e to the x, 2x dx. This is v du. You probably wondered, how is that going to help us? How is that going to help us? Well, it actually helped us a lot because we had a, let me finish writing this one more step, then so I'm going to bring 2 in front, so that's a 2. I'm going to bring x in front of e to the x, so 2x e to the x dx. So it helps us a lot because in this integral, we get x e to the x, but the one we begin with, we had an x squared e to the x. So this part is simpler than x squared e to the x, because we make the x squared into an x. We lost one x there, so that's a good thing. But we still have this integral, so we have to continue to integrate until we get rid of all the integrals, right? So the next step, so let's leave it here, but let's just focus on the integral. So next, focus on integrating x e to the x dx next. And then we can just substitute it in there. That's what we're looking for, right? So here again, I'm going to use u and the v again. So I'm going to let u equals x. I'm going to let dv equals, so this is the u, this part is dv again. So dv is e to the x dx. So from there, I can figure out du, which is dx. V is the integral of dv, so that's the integral of e to the x dx, which is just e to the x. And with those 4 terms, now we can apply the integration by parts again, just for this integral x e to the x dx term. So that becomes, so integral x e to the x dx becomes u times v, which is x, so maybe I should box them. So u, v, du, dv. So those are the terms that we might need. So u times v is just x e to the x. And minus, it's always a subtraction, minus integrating v, which is e to the x. And then du, which is dx. You see, at this point, it's really nice because we get rid of the x. We still have an integral, but compared to x e to the x, we just get e to the x, which is a lot simpler. So that's a good thing. And then we can integrate directly. So that's a x e to the x minus e to the x. And obviously that's a constant c you can add to it. So that's the antiderivative of integrating x e to the x dx. So if we have that, we can bring it back into this part because we haven't figured. So that's what we need to replace. So the original integral, so let me just copy it down, integrating x squared e to the x dx, that's what we integrated in the beginning. We got, using integration by parts the first time, we got x squared e to the x minus 2 integral x e to the x dx. Then we focus on this integral alone. We got an antiderivative for that part. I'm just going to put it in here. I'm going to rewrite it. So we got x squared e to the x minus 2 times this integral that gave us x e to the x minus e to the x plus a c. And then now we're just going to expand the parentheses, distribute the -2. So we get x squared e to the x minus 2x e to the x minus 2 times the negative. Use a different color. So we distribute the -2 here, distribute the -2 to this term, and distribute the -2 to c. We got plus 2e to the x. Now we're going to have minus 2c. You can just write as a different c. But this is the antiderivative we got at the end. Like I said before, this minus 2c, you can just call it a different c. So it doesn't matter if it's minus or plus, you can just write a plus with different c. At the end. So I want to, this is an example I just want to show you because it's, you have to you use the integration by parts first time, and it helps a lot. And then, but it doesn't take you to the final answer. Then you're gonna have to just look at the integral part and then focus on that part, and then apply integration by parts again to get to the final antiderivative. Sometimes you probably use the integration by parts once, then you get something. In some example, at this point, you can try to use u-substitution or use some other approach. You don't have to use integration by parts second time, but it just depends on the problem that you end up with. But the procedure is that you always take the given integral, you always identify the u and the dv. So sometimes you have to, if you have product, you have to decide, okay, which one should be the u, which one should be inside the dv. You try it, it doesn't work, then you switch them around. Right, try again. But generally speaking, because you always want to end up with something simpler in the integral, so if you have if you're integrating x to the power, x squared or x cubed, and then some function f of x dx, if you have this setting, you always want to let u equals x to the a, and then you want to let dv equals f of x dx. Because the benefit of setting u and the dv in this form is that when you find du, you get ax to the minus 1, ax to the a minus 1 dx. Just erase this, I'm getting caught here. So you get ax to the a minus 1 dx, and the dv is just f of x dx. So the benefit of this is that the du you're going to need in this part will have the x term will have one power less, one less in the exponent. So that's a benefit of that. Generally speaking, that's what you're going to try to. That's what you always set u to be if you have that set up. All right, any questions on this example? I know there's a lot of information going on. Just do your best on those. I haven't decided yet, I might post a very small homework just on this section for you to practice. But again, I'll give you 1 week, right, to practice. If you can try to get ahead on that if you don't have too much to do. Any questions? If you haven't done the second homework yet, definitely get started on the second homework, because that homework will help you a lot on the quiz that's coming up on Thursday, because that's a lot of problems that's practicing finding the volume using different approach.